recent highlights of research in that area, especially concerning kinetic mixing implications, but also going a bit more into the astroparticle phenomenology. And to start us right off, the question that I want to raise at the beginning is, of course, why, I mean, dark photons already imply it's not standard model physics, so why should we even go beyond the standard model? And I mean, the obvious two reasons for me are, first of all, basically that we have confirmation, albeit indirect, that there must be some other form of matter which we cannot explain by standard model physics, namely the dark matter. So that is, of course, a big open question. Like, if dark matter is consisting of particles, what kind of particles are they and how can we test them? Not even touching dark energy. But then even if we look at the energy budget of our universe and we only consider the part of, let's say, the matter that we understand, which is roughly 5% of baryons and neutrinos, even in this sector that is in principle described by standard model, there's something funky going on with the neutrinos. Because we know that in the minimal standard model, the neutrinos only have a left-handed spinor representation, and there is no singlet representation of them. And this is a problem because this means that they must be strictly massless. But of course, since, well, decades ago, we already know that there must be neutrino oscillations, which are only possible if these particles are massive. So for sure, there must be some mechanism that can generate neutrino masses, which is not part of the standard model. So we have very clear motivation to think about extensions of it that can address some of these issues. And if we zoom out a bit and think about the landscape of theoretical physics, theoretical physics in kind of a cartoon drawing, then we can imagine the following picture. So if we think about what we have in terms of the two guiding principles, then there is, let's say, we have a lot of experiments that push towards the high energy frontier, and they are basically originally were motivated, of course, a lot by, for example, supersymmetry or grand unified theories, or maybe, let's say, even string-inspired models. But also we can have an orthogonal dimension, which is basically pushing the intensity frontier. So we're trying to test weaker and weaker and weaker interactions. And if we span this plane of, let's say, energy versus intensity, then we can place our, let's say, experimental probes here, where at the high energy frontier, we have, of course, collider physics. And at the moment, most interestingly, of course, the LHC. But also in the past and even recently, there is a lot of interest in meson factories where we can test the QCD, but also beyond standard model physics at higher intensities, as well as beamdams where we can produce a lot of particles by basically impinging charged particles into a target. And then if we go to lower energies, but basically testing higher intensity, or let's say smaller couplings, of course, we have a lot of precision experiments or also astrophysical and cosmological observables. So if you look at this 2D sketch, then you can, of course, say that we see something like an intensity frontier here, which is along the diagonal of this plot. And basically, if we take this, we can see that basically we have a motivation to look for physics that with smaller coupling also has smaller mass, because this would exactly explain, or let's say, this would motivate to push along this intensity frontier or the sensitivity frontier of our experimental landscape. So the question is, are there well-motivated theories that can do this for us? And I want to argue in a minute that yes, they are, and they are, for example, extra gauge bosons. So with this motivation, let me quickly give the outline of what I want to convey today. So I want to start by reviewing the dark photon as one of these particles that can exactly be lying along this sensitivity frontier. But even going beyond the minimal case, where we just consider a simple vector portal, you can have more rich theories where you have basically these anomaly-free model constructions where part of the standard model fermions are also charged under the dark sector symmetries. And something that is going on right now is I'm working with a student on basically also looking at gauge boson contributions that can basically introduce this portal at the one loop level by basically contributing loop contributions to kinetic mixing. And to tie all of this together, an application for this to phenomenology is basically Higgs decays to exotic final states that contain, for example, one or many dark photons. And then I want to conclude with basically an application of all these models in stellar physics, or let's say in astroparticle physics, namely stellar cooling, or more specifically white dwarf cooling. And as you can see here, if you ask ChatGPT how a dark photon looks like, this is what he gives to you. So at least we have a rough idea what we're looking for. Okay, so let's start with a little background of the dark photon. So what is the dark photon? Essentially, the dark photon is a very simplistic model where you consider an extension by a new extra U1 symmetry of the standard model. And because this is abelian, there is a particular feature of these theories that basically the field strength tensors of these models are gauge invariant by themselves. So you can introduce a coupling where you have here basically a mixing between the standard model photon and the dark photon. And now if you consider that the potential dark photon is massive, but its mass is lighter than the typical weak scale, you can basically diagonalize the kinetic terms to define, let's say, on-shell mass propagators by just doing a simple field redefinition of this kind here, where you shift the standard model photon field by a small fraction of the dark photon field. And what this means in terms of interaction is that basically this dark photon particle, which I labeled X here, picks up a coupling to the electromagnetic current, but with a suppression factor of this kinetic mixing epsilon. So essentially, that's why it also is called a dark photon, because it couples exactly as the standard model photon, but suppressed by epsilon, and it has in principle a mass. Also, if you consider UV constructions of these models, then typically this kinetic mixing is introduced by some loop process. So let's say a generic order of magnitude estimate is that this epsilon should scale like a new coupling constant divided by some loop factor, which motivates why these kinetic mixing portals are generally very small. So if we consider some kind of portal like this, then if indeed this is massive, the way that you can acquire mass, if you inspire it by the standard model, is by Higgsing this new symmetry. So meaning you have a new scalar that acquires a VEV that is charged under this symmetry. And then this will lead to a mass term like the one that I've written down here. So basically what you get is you introduce a mass that is proportional to the coupling constant and the VEV of the scalar. So naturally, if you tune down the coupling, you will also tune down the mass. So these bosons naturally lie, or let's say, they have a natural relation to be hiding exactly at this sensitivity frontier that basically if you tune down the coupling, you have to go to higher intensity, but also it means that the mass will be smaller. So these are very good targets to look basically everywhere. And so why is this all interesting? Because what we want to consider now is basically how this kinetic mixing comes about. So of course you can just, let's say, close your eyes and write down a portal with the photon. But we know that this, like the mixing with the photon, cannot be fundamental because the photon is basically a superposition of the gauge states of the hypercharge and the neutral boson of the SU2. So if you want to consider a UV complete model, you have to introduce the mixing with the hypercharge boson. And you can, of course, by symmetry, allow a tree-level term, but you can also introduce it at the loop level. And what then will happen, basically, if you consider that your theory after electroweak symmetry breaking and you decompose your hypercharge boson into the mass eigenstates, you will not only have a mixing with the photon, but you will also have a mixing with the Z. So basically, if you want to have a UV complete construction, you will have both of these portals generically. But let's say this is the the lowest order picture of these models. But I want to argue that basically this is not enough, because there is, in principle, a dimension 6 operator, which will introduce also mixing between the dark photon and the neutral component of the SU2. So if you consider this operator here, you have two Higgs doublets coupling in a singlet representation to in a triplet representation to the W fields, making an SU2 singlet. But after electroweak symmetry breaking, essentially you will get just the only term that survives is basically a mixing term between the W3 and the dark photon. And what this gives you, of course, because we know that the W3 is also a superposition between of the photon and the Z, you will again generate kinetic mixing terms between the photon and the Z. So basically both of these operators, the fundamental mixing between the U1 hypercharge and the dark photon, and this higher order W mixing with the dark photon will generate you the kinetic mixing terms between photons and Z bosons. Of course, you could say, yes, this is a higher order effect. I don't have to worry about it. But what I want to argue in the next couple of minutes is that basically in most of the well-motivated dark photon theories, this operator is introduced at the renormalizable level. So basically at dimension 4. And how is this happening? So basically, if you have this operator, you can in principle, like once you have taken your electroweak symmetry breaking, you can basically compute the loop-induced mixing as usual by just identifying the vacuum polarization amplitude with the kinetic mixing parameter and apply standard techniques to compute the one loop mixing, where now the only thing that changes to the standard law is that you don't take, for example, the electromagnetic charge of your fields running in the loop, but you take the SU2 charge. Basically, the T3 generator is entering here. But now, if we go away from the simple kinetic mixing scenario and we consider more rich models where we also allow standard model fermions to be charged under the new symmetry, we will see that we can basically introduce these portals at the renormalizable level. And to do this in a systematic way, we can just consider all the standard model fermions that are available. So basically we can order them into the quark and lepton doublets and all the singlet fields. Oh, sorry. So for some reason I don't have a mouse available. That is a bit annoying, but okay. Anyways, so let's say we consider the most general setup where we allow now the dark current, the dark sector current also to include standard model fermions. And if we want to be as generic as possible, we have, of course, to consider the scenario where all of them can have a charge. Then the theory guiding principle tells us for any good symmetry, for the theory to make sense, we have to cancel all the gauge anomalies. And here in the table at the bottom, I have listed basically the conditions on the charge choices that all the different gauge anomalies give you. These X's for clarity, these are the power sums of all the charges of all the fermions. So, but you see, this is a very complicated system of equations. But we have more information because we know, of course, that standard model fermions, they get their mass from the Higgs mechanism. So we have to also be able to write down the Yukawa couplings as in the standard model. So these should also be allowed by the new symmetry. And this reduces the system of equations quite dramatically. So basically, this reduces it to 3 equations where we have basically these green ones, which give constraints on the lepton charges. And the red ones, they are basically the same equations telling you that the sum of the lepton charges has to be a third of the sum of the quark charges. So now we have already quite a restrictive setup for our general theories. And now we can consider basically 2 setups, 2 scenarios. The first one is if we allow the neutrinos to have Dirac masses, so we exclude any Majorana mass term, we can do more because in principle, the Yukawa terms of the standard model, they allow for 3 different classes of charges, which I have written down here. So either all of the families have the same charge, or two of them have the same, or they're all different. And now if we assume that the SU2, like the doublet and the singlet representations are always having the same charge, then we can now diagonalize the mass terms. And we see that, of course, as in the standard model, we will introduce these CKM and PM&S matrices, which basically tell you how mixing works. And this gives you an additional set of constraints now, because the way that you now can write down these CKM and PM&S matrices with your mass terms, these give you a constraint on the charge contributions. And especially if you don't allow for Majorana mass terms for the neutrino sector, you can only allow for the A cubed charge assignment, meaning all of the leptons have to have the same charge. And this basically only leaves one choice for your new symmetry, namely the B minus L. So if you want to have Dirac neutrinos, strictly Dirac neutrinos, the only thing you can do by having a phenomenologically viable PM&S matrix is to have a B minus L extension. Then the second case, of course, is you have more freedom. You allow also Majorana mass terms, and then you can construct more theories. Especially you can construct these lepton flavor number symmetries and the B minus 3L symmetries and combinations of those. But one interesting feature in these theories is that basically, if you allow for a Majorana mass term, now you will see that basically these matrices don't commute anymore. So let's say the fermion diagonalization matrices are not commuting with the charge matrices anymore. And what this does for you is it introduces off-diagonal neutrino couplings. So this can basically introduce neutrino decays. And that's basically a general prediction of these models, which could be interesting. But of course, the problem is if you want to compute the neutrino decay rate, you see that this is basically suppressed by at least a factor of chi squared times m over like neutrino mass over mediator mass to the fourth power. And this makes it, of course, extremely rare and very hard to test. Okay, why am I telling you all of this? So we have seen that we can construct these general models, but what all of them share, all of these models share, is that necessarily they give charge to the SU2 doublets. And now if you think back what I told you 10 minutes ago is basically as soon as you give charge to SU2 representations of the fermions, you will introduce this W mixing operator at the renormalizable level. So what this means is that for all of these phenomenologically, let's say, well-motivated and highly studied cases, you will introduce a W mixing at the dimension 4 level. So you have to take into account W mixing if you want to have a UV, let's say, a consistent UV construction of your kinetic mixing terms. And to be more concrete, let's go through one example. For example, the L mu minus L tau. So what you can, of course, do is you say, I'm not interested in UV physics. I just want to compute my mixing with the photon at low energies. If you do this, you follow standard procedures, you will get a mixing term which looks like this, which is basically sensitive to the log of the mass ratio and the product of the gauge couplings. So if you want to reproduce this from the UV picture, if you do the naive thing, if you calculate this loop now, what you will get is some weird combination of the ratio of the charged lepton masses times the ratio of the neutrino masses. And of course, this does not reproduce your naive expectation of I'm just decomposing the hypercharge boson into its photon mass eigenstate, and then I should get the right answer. So this is not working. But we know exactly why, because we have to be more careful, because we also generate the W mixing. And if you compute this operator now, where you know that, of course, only the SU2 representations can run in the loop, you will get exactly the matching terms to cancel off the neutrino masses and to give you the right numerical factor to reproduce your naive IR computation. So basically, you can match the IR with the UV, but you have to be careful to also take into account SU2 mixing. But the story doesn't end here. Once you open this box of looking also at mixing with the SU2 components, you also have to wonder what actually happens with W bosons running in the loop. Because, of course, we know that the photon has also a W3 component, and the W3 has self-interactions with the SU2 gauge bosons. And this is something that basically can also contribute, and this is something that's coming right out of the press. This is a project I have been looking at with my student, who has basically handed in his thesis yesterday, so you are the first ones to see these results. And I want to generate a bit of excitement here, just because of the, let's say, the novelty of this formalism. And the idea is the following: if you have a generic gauge symmetry at the Born level, so at the lowest order in your expansion, you can always define a matrix element in the current structure. That's basically, for example, how the Fermi theory works, or how we basically learned about these intermediate states. We just defined these current interactions, and then if you can resolve the propagators, you see that basically they are connected exactly by this propagator structure. So a generic form of your amplitude looks like this. You have a gauge current connected via propagator to another gauge current. But if you go to, like, if you consider quantum corrections at the one loop, you will receive corrections to all of these structures. You will have these bubble corrections to your propagator. You will have the triangle corrections to your vertices, and you will have an irreducible box correction to the 2-to-2 process. And now, if you want to consistently take into account all of these corrections in your amplitude, which in the end will give you the physically valuable information of observables, then you can basically extend your naive Born level current picture by also incorporating one loop corrections. So you basically you incorporate also the triangles here, giving you a correction to the vertex. You incorporate the bubbles into your propagator, and you have an additional term which is not there at the tree level, which is basically coming from the irreducible box correction. So if you consider this dark photon extension, you can do this in a matrix, in a vector matrix way, where you introduce all of your gauge currents, and you will see that, of course, only the SU2 currents receive these triangle and box corrections, because you don't have these at the Abelian level for U1 symmetries. Now, what you can do to basically, let's say, recover your naive current structure is you can linearize these equations. So basically, you expand these amplitudes consistently up to order G4, which is the one loop order in your couplings, and try to recover a structure that looks like the one we had before. So you want to recover the current propagator current structure. And you can do this by basically linearizing these equations, and by changing then finally to your what then defines the mass eigenbasis of your vectors. And you will recover a form of your propagator matrix that is quite familiar of what you would get in an electroweak theory. Basically, what you have is you have on the diagonal, you have the inverse propagators with their self-energy corrections. And on the off diagonal, you get mixing contributions. And these mixing contributions, they are now basically a sum of your naive bubble corrections, but also of terms which go like the inverse propagator times the triangles or the boxes. And the beauty of this theory is, I mean, of course, this is all standard law for electroweak symmetry renormalization. The beauty of this formalism is that the response, let's say, the term that you will compute in the end is gauge invariant in any gauge choice that you do by construction, because it is the term that you extract from the amplitude. And amplitudes are physical quantities, so they must respect gauge invariance. While, for example, if you do the naive computation of just including your bubble corrections, as you would do for fermions, then your answers would be gauge dependent, because you are basically leaving out terms in the amplitude that cancel the gauge dependence. So this is basically the correct way of computing the gauge boson contributions to a one loop enhanced amplitude. And as we can see already, we need to include all the bubbles, all the triangles, and all the boxes. So of course, this is a big loop fest. you have to be careful that you don't forget any diagrams. And to make gauge invariance manifest, the way that we went about is to compute all of these contributions in a general arc-C gauge. So not doing any gauge fix, sorry, not gauge fixing, of course, but not taking any gauge choice, so that in the end we are sure that any potential gauge dependence in your final answer vanishes. But then, of course, you have to be very careful to take into account ghosts, to take into account Goldstone bosons, and even tadpole diagrams, which usually in the literature they are omitted, but they are actually non-vanishing and they are an integral part for your gauge cancellation. And then, of course, you also have to take into account these one-loop triangles and boxes that correct your vertices, and I mean the irreducible 2-to-2 process. So now that we in principle know what are the ingredients for the gauge boson corrections to kinetic mixing, we can basically derive the answer from our propagator matrix formalism. And specifically, we can compute now the general mixing of a photon with a dark photon and the set with a dark photon by taking into account all of these contributions and summing them up correctly. And to just give you a nice compact example, this is basically the result that we would get for the photon dark photon mixing, where you can see now that this result, although computed in a general arc-C gauge, is manifestly gauge invariant. All the gauge dependence cancel in the final answer, and you can give a quite compact result in terms of the irreducible Passarino-Feldman functions. So what you get is basically an answer for taking into account all one loop level SU2 corrections, which are gauge independent and only depend on the W mass as the only degree of freedom that can run in the loops. Okay, so this is, of course, let's say, technically very nice. But now you might wonder, why am I telling you all of this? This is maybe something for QFT enthusiasts, but why should I worry about this? And the point about all of this is the Higgs low energy theorem. Because once we compute all of these 2-to-2 processes, we can make use of the Higgs low energy theorems to derive generic Higgs decay amplitudes to bosons. And the way that the Higgs low energy theorem works is that basically the Higgs to 2 boson amplitude is linked to the 2-point function via the derivative by the VEF. So essentially, if we compute to a given order all the amplitudes of, let's say, like all the 2-point boson amplitudes, we get the Higgs decays for free. And that's, of course, a very powerful tool, because we know already that from what we have computed so far, we can write down a one-loop enhanced Lagrangian where we have all the 2-point functions of the bosons available now. And with this formalism, if we look at this one-loop enhanced Lagrangian a bit closer, we can identify 2 mixing contributions. The one, of course, is the kinetic mixing, the ones like the amplitudes that I have basically been showing you for the last 20 minutes or so. And there can, in principle, of course, also be a mass mixing between the Z and the dark photon. With these one-loop results available, we can now, of course, diagonalize our Lagrangian to derive the now would-be eigenstates at the one-loop level, the mass eigenstates. And if we do this and take the consistent Higgs low energy theorem, we can compute the general Higgs to 2 boson amplitude by just plugging in our expressions into this formalism. And the way the Higgs amplitude works is simply the derivative of the gauge, like of this diagonalized vacuum polarization matrix and the derivative of the diagonalized mass mixing matrix. And if you look at this, if you apply this diagonalization to leading order in your kinetic mixing parameter, you see that you will recover always the tree structure times a mixing, times a tree times one loop mixing. And so what does this mean concretely? If we look at a simple example, for example, if we look at extensions of the standard model that include a baryon number symmetry. So let's say generically you couple to the baryon number. Then you can apply the Higgs low energy theorem to derive all of these Higgs decay amplitudes. And the only thing you have to do is to derive the one loop kinetic mixing amplitudes and take the derivative with respect to the VEF, where now only the top quark plays a role because it's the only one that is heavier than the Higgs and survives in the low energy expansion. So we can make generic predictions for Higgs decays to, for example, a photon and a dark photon in any of these baryonically charged models. And if you look at this, we have, for example, derived the branching ratio of Higgs to photon, dark photon, taking into account the fermion contributions. So you get a generic answer in terms of the fundamental gauge coupling and the tree level kinetic mixing parameter. And if you plug in some order of magnitude estimates for what this coupling might be, then you can see that the branching ratio that you would observe is something that is in reach of the FCC-HH. So in principle, this could be a channel to look for exotic physics in a Higgs factory. And I mean, the next step, of course, is to include also the gauge boson loops to see if you get an enhancement in this in these amplitudes. Okay, after all of these theory exercises, I finally want to come to a bit more phenomenology. And basically, having already mentioned the lepton number symmetries, I want to motivate from a phenomenological point of view why these are interesting for us. And so, of course, we know about this G-2 anomaly, which has been discussed a lot in the community, basically also because there are, let's say, disagreements in the theory computation of the G-2 contribution in the standard model. Basically, if you compare these dispersion relation methods to the, sorry, I'm missing the word now, to the lattice computations, there is a substantial disagreement, but in principle, they are not compatible with the standard model, depending on who you believe. But let's say, even if you take the most optimistic case, it seems like there is still some kind of disagreement. Anyways, if we take it at face value, we trust the traditional dispersion relation computations, we see that the standard model value is disagreeing with the experimentally found value by something like 5 sigma. Of course, as I said, don't take this at face value, but I just want to highlight that there might be a discrepancy still. And now you might think, okay, let's assume it really is not standard model physics. How could you explain this deviation of the G-2? And of course, here these leptophilic bosons can come into play. That basically already at the one loop, you get a correction to the G-2 of the muon from having now a dark photon contributing to your dipole moment, sorry, to your magnetic moment via this triangle process here. And if you look at the typical, let's say, the typical plane of coupling versus mass of these models, you can see that although there have been substantial progress by, for example, Na64 mu, there is still some part of parameter space left where you can explain the G-2 anomaly that has not yet been tested by any experiment. So in principle, these theories are still an option to explain the discrepancy. But then the question is, okay, how can we basically rule out the remaining part of the parameter space? Like what kind of observables can we construct that can test this explanation? And I want to argue that one observable which you can, which is very sensitive to this, is basically the neutrino cooling rate of white dwarfs. And to motivate this a little bit, let's have some brief introduction, or let's say a brief recap of how white dwarf cooling works. So white dwarfs are stars that are typically formed after a conventional star has exhausted all of its fuel. It has burned all of its fuel, but it's not massive enough, for example, to collapse into a black hole or to explode in a supernova. Then it can form a very dense white dwarf. And essentially, a white dwarf is like a core, a stellar core, like just one stellar core without outer layers, mostly composed of carbon and oxygen, and is very dense. It's typically 10, like one order of magnitude denser than the core of our star. So that's the average density. And it's therefore also, at least in its birth phase, it's hotter than our sun, for example. And there are basically then two different processes that can cool down these stars. One is, of course, surface cooling by photons, like, of course, also we have in the sun. And the same process that we also have in the sun is basically that we can produce neutrinos in the stellar core. But the difference here is that white dwarfs are much more massive, and therefore they can produce neutrinos in the beginning phase also more efficiently. So basically, in the hot phase, the neutrino cooling is dominant, while in the cold phase of the star, you're basically only losing energy via photon emission. So then, if we consider this early phase of cooling via neutrinos, we have to understand what is the typical process that dominates this. And in the standard model, the process that produces neutrino cooling is the plasmon decay. So what happens is basically you produce photons everywhere in the interior of the star. But since you have a thermal plasma of electrons around, the photon can basically produce an on-shell loop of thermal electrons, which then allow you to decay into two neutrinos. And in the standard model, of course, we know that everything that couples to neutrino has to be the weak theory. So basically, there are these two different processes with the W and the Z. And if we compare the typical energy scales in a white dwarf, we know that the typical energy scales, which are KeVs, are much, much smaller than the mass of the W and the Z. So for any relevant computation, we can just take the Fermi theory limit where we integrate out the W and the Z boson. So we have only an effective vertex to take into account when we compute the amplitude for the cooling rate. If we now consider a dark photon to be around that has some coupling to neutrinos and electrons, we can, of course, reproduce the same kind of plasmon decay. But if we allow the dark photon to be lighter than the heavy bosons, then, of course, we have to be careful with the thermal propagator of the dark photon. And the point is, of course, the following, that you have to be consistent to take the full thermal propagator of the dark photon when it's produced in the sun, by taking the Dyson sum of all of these thermal loops. Essentially the same that you would get for the standard model photon. But now, of course, the couplings here are different because you have a massive particle that has now a new dark sector coupling. But you can compute these Dyson sums, and the result, since you are now in a thermal plasma, will behave differently for the longitudinal propagational mode and the transverse. So you can split the full propagator into the longitudinal and the transverse part. And then you will see that basically your thermal mass, you will get a correction of a thermal mass, which in the longitudinal case is just the zero components of your vacuum polarization tensor. And for the transversal, it's the spatial components. So we know how to compute the thermal propagator in principle in this theory. But now we can just try to brute force repeat the same calculation that we do for the standard model by defining something like an effective 4 Fermi operator, although we will retain the energy dependence of these operators. And then we can, of course, apply the same computational techniques by just shifting the coupling that we have in the standard model between the electrons and the neutrino by this Q-squared dependent contribution from the dark photon. And of course, we have to keep track of longitudinal and transversal modes. Then if you look at the typical plasma frequencies of a white dwarf, which are plotted in the upper right corner here, then you can identify a couple of different regimes. So what you see is that across the radius of the white dwarf, starting from the inner core, the plasma frequency can go as high as a couple of 100 keVs. So this example is for a white dwarf which has a solar mass and 10 to the 8 kelvins. So you can see the plasma frequency is of order a couple of 100 MeVs, but as you go outside of the star, And basically going to the outer layers, the plasma frequency drops with the radius until it basically almost is vanishing completely, or let's say going to zero at the outer radius, and you have a cutoff at around, let's say, 200 electron volts. So depending on where you are with your mass of your new mediator, you have three different regimes. If the mass is much heavier than the temperature and the plasma frequency of the star, you can exactly reproduce the standard model behavior by just integrating out the intermediate dark photon in this process. If on the other hand side, the dark photon is much smaller than the plasma frequencies, then you can just forget about the mass completely and you recover the photon regime. So this is what we would call an ultralight regime. And then, of course, there is the nasty bit in between where your dark photon mass is comparable to the plasma frequencies. And then something can happen which makes the process a bit more involved, that namely, depending on where your mass exactly lies, when the dark photon propagates through the layers of the star, at some point it will hit exactly the resonance of the plasma frequency. And then, of course, your propagator goes on resonance, and you need to have a regulator to compute this process. But we know, of course, how to do this. We need the Breit-Wigner propagator, which for some reason seems to have disappeared. No, here it is. So we need a regulator in our propagator that our amplitudes are still physically consistent. But we know how to compute the Breit-Wigner propagator. We have to take the imaginary part of our vacuum polarization amplitude. And for the dark photon, especially if it's like, since we want to introduce neutrino cooling, we know that we have a coupling of the dark photon to neutrinos. So meaning that it can always decay into neutrinos. And this exactly will introduce an imaginary part of the vacuum polarization amplitude. And since we are in a white dwarf where there is no thermal abundance of neutrinos, we can compute this contribution in vacuum. So there is no thermal loop of neutrinos. So we can take the standard techniques to compute the neutrino contribution to the vacuum polarization amplitude, and then split it again into longitudinal and transversal part to get our regulators for the Breit-Wigner propagator. So with this prescription, we can compute our cooling rate throughout the star for any mass of the dark photons. And finally, I want to show you some plots here where you can clearly distinguish these three regimes. So again, it's here the limit shown for extra cooling in the range of the dark photon coupling and the dark photon mass for an L mu minus L tau scenario. And if you are at masses which are very low, specifically below these 200 EVs that I showed you before, your dark photon behaves like a massless boson, and it's basically the limit. The exclusion limit is universal. So this is the ultralight regime. Then you see this intermediate range where you have to be very careful to keep track of the propagation through the star, since your dark photon can hit the plasma frequency, and you have to take into account all these thermal processes where you can go on resonance. And there you can see a significant enhancement of your limit, simply because once you hit the plasma frequency, you will get an enhanced production of neutrinos through resonance. And then finally, once you are going to masses, let's say above order hundreds of keVs, your mass is much heavier than any of the relevant energy scales in your star, and you can basically just recover the massive regime where you don't have to care about the temperature at all. So now with this general result, we can basically look at this interesting phenomenological regime where we can explain in principle a G-2. And what we find is that with the current best limits on neutrino cooling from white dwarfs, which lies at 30% extra cooling over the standard model, we actually see that we can exclude part of this regime, and we get the leading limit here from, let's say, in this diagonal direction for small masses and small couplings. So in principle, if with future missions, which are aiming at observing a lot more white dwarfs than we have currently observed, if we can get more accurate estimates on the on the neutrino cooling of white dwarfs. And if we could improve by something like even, let's say, an order of magnitude, which of course is a lot in the cooling, but let's be optimistic, then in principle we could almost exclude completely this region of the G-2 explanation by white dwarf cooling. Yeah, and with this little phenomenological outlook, I want to conclude already my review of the dark photons here. And just to repeat a little bit what I tried to convince is that, first of all, if we consider dark photon extensions, we have to be careful if we want to have a UV complete construction, which is consistent, to also include mixing between the dark photon and the SU2 components. And basically, this means that your prescription of matching the IR mixing with the photon and the Z to the ones with the hypercharge and the W, you have to take into account the sum of the two mixings as prescribed here. Yes, essentially, this mixing with the W is crucial in all of these phenomenologically interesting models, simply because they always give charge to SU2 multiplets. Then something that we are just starting to do now is to also include loops coming from the gauge bosons themselves. And we saw that they are non-negligible and can be especially relevant for Higgs decays. And in general, I also want to advertise for this Higgs low energy theorem to be used in terms like to compute these Higgs decay amplitudes for general boson decays via just computing the kinetic mixing contributions. And finally, some phenomenological result is that white dwarf cooling due to these L mu minus L tau bosons are sensitive to the G-2 solution in terms of these models, and it could be an interesting direction to exclude this in the future. And with that, I want to conclude my seminar, and thank you very much again for inviting me and for your attention. Thanks.
Thank you very much, Patrick, for the very nice and very complete talk. Question from the audience?
Yes, I have a question.
Yes, continue.
First, thank you very much, Patrick. Very nice presentation.
Thanks.
Regarding the Higgs low energy theorems,
Yes.
is there an assumption on the scalar sector of the theory? Or
not specifically. I mean, so yes, let's look at these. So there is no specific assumption on the scalar sector, but there is an assumption. Well, okay, there is, let's say, these results that I presented in the beginning, or especially, let's say, these results. So this equation here, this is completely general. This has no assumption. But as you can see here, of course, what I'm showing you here is that this decay amplitude also includes contributions from the mass matrix itself and the mass mixing. Now, if I wanted to show you these concrete results here, there the assumption was that, for example, there is no standard model contribution to the dark photon mass. So the Higgs remains uncharged under the new symmetry. And also there is no fundamental, there is no fundamental mass mixing in the theory. So that basically only the vacuum polarization amplitudes contribute.
Okay, so in the previous slide, the mass
Yes.
mixing is
this delta
taken into account. Okay. And then in this next slide, for instance, in this branching ratio expression, if we
Yes.
include mass mixing, we could expect some contribution from the VEV of the extra Higgs and so on.
Not from the extra Higgs, because remember, so I mean, okay.
I mean the Higgs that is responsible for the breaking of the U1x.
Yes,
U1 primes.
so this would be a next to leading, or like in this expansion, it would be higher order, because if you consider you have an extra scalar that also mixes with a standard model scalar, if you want to have a contribution from this mixing, then you need first the scalar mixing to mix the standard model Higgs into the dark Higgs, and then apply the Higgs low energy theorem for your dark scalar. So this would be, let's say, next, like one order higher in your expansion. But of course, if you have mass mixing there present in general, you will see something like at the bottom here, where you have these results from, for example, you get a contribution from the mixing between the dark photon and the Z. And if these carry some contributions from the standard model scalar sector, this will give a direct contribution to your decay amplitude. Yes.
I see. I see. Thank you.
Thank you.
More questions from the audience? Patrick, I was wondering, for example, in this model, when one has this local U1x symmetry that should be broken by some scalar, maybe a scalar singlet will be the simplest one.
Yes.
But that scalar singlet, it will couple trilinearly with this U1x, U1 prime gauge boson, with this X gauge boson. So you are assuming that this extra scalar will have tiny missing with the Higgs. So there will not be this extra scalar contribution to the kinetic missing at one loop level.
That's a good point. Yes. So let's say in what we have done here with, for example, with these amplitudes, we have ignored the dark scalar for now, because of course you're absolutely right. If you want to be completely general, you would have to consider a scalar portal as well. And then, I mean, in principle, you could have mixings here with the dark sector. But these again would be higher order, because you would have one more mixing to introduce to construct these amplitudes. Because like the basic principle of all of these is just based on the SU2 left symmetry. Because I mean, it's all like, it breaks down to all of the mixing components coming from the W3. Simply because the simply because the dark photon mixes with the W3 of SU2. So that means that all of the mixing amplitudes you have in SU2, you will also get with the dark photon. But then if you consider an extended scalar sector, you are right that at least, let's say, to some order, you would also have to consider mixings through the dark scalar, and all of this picture would get more involved.
But maybe there will be some leading effect, because this precision, imprecision.
There should be one order higher than, let's say, these one loop effects, because you would have the one loop from the gauge structure times a mixing. So it would be one loop times a mixing. So it would be one order higher in your expansion in the couplings.
Another question: have you considered, for example, collider signature? Because in principle, if one has this extra scalar, which could decay into this extra scalar, which I would assume to be light, because this dark photon, this there will be a small bag for the breaking of U1x. This extra scalar may decay into dark photon, may have decayed into dark photon pair at one loop level. So in principle, there should be maybe displaced vertex in the collider, or
yes to everything. This is something we are studying at the moment. There has been some initial work by Renata Funchal and company, who have considered the combination of a dark photon and the scalar sector. But yes, we are also trying to understand what are the collider implications for that. And unfortunately, or fortunately or unfortunately, there is no simple answer to this, because it depends a lot on the relative scales between the scalar VEF to the electroweak sector and the masses of the dark photon. So of course, if the dark photon is light and the scalar is heavy, you cannot produce it easily, so you can only produce it indirectly. But then, as you say, if in principle there is a decay channel open, you can also produce scalar decays. You can produce basically Higgs to scalar decays. Yeah, in principle, this allows for a very rich phenomenology. And you're absolutely right that if the couplings are small, you will also produce displaced vertices from scalar decays. We're working on this, but yes, it's let's say it's very rich, and there are very different scenarios to take into account to get a complete picture of how the phenomenology looks like.
Thank you.
Thank you.
Thank you so much. More questions from the audience? If there are no more questions, we thank Patrick for the very nice and very complete seminar. Thank you so much, Patrick.
Thank you very much for inviting me. Bueno, buenas tardes. Que le vaya bien.
Buenas tardes. Have a nice time.
Thank you.
The next year we will have a biannual workshop in January. In the week of the 4th of January will be nice if you can come and give a talk at the high energy physics annual seminar that we used to have.
I mean, I would be thrilled to come. The only thing, of course, is I have to find out about the travel money.
I say yes, it's a bit yes expensive.
But yeah,
nice.
I would be definitely very happy to come. Yes. Thank you very much again.
You're welcome. Thank you so much. I see you.
Thank you. Bye.
Bye. Bye.
Bye bye.
Bye.
Bye.